Percent yield is defined as actual yield divided by theoretical yield times 100. Please make sure that you are memorizing this formula. You must know how to calculate percent yield. Um, there are very set steps that you can follow when determining percent yield. Let's look at an example of an equation that we worked with at the end of last session. First step whenever you're going towards a percent yield is to balance the equation. And if you remember from the previous session, we balanced this equation as TiCl4 plus 4 sodium gave us 4 sodium chloride plus 1 titanium. The next step in the process of percent yield is for us to determine the limiting reactant. Now, based on the amounts that we were given in the previous problem, these amounts were using 965 grams of TiCl4 and 480 grams of sodium. Based on those amounts of the reactants given, we determined in the previous session that the limiting reactant will be TiCl4. So based on that, the next step, therefore, is to determine the theoretical yield of the product titanium, which we also determined in the previous session as 244 grams of titanium. Now, please remember that the theoretical yield is the maximum amount of, in this case, titanium that can be produced. And can is the important word. But will it be produced? When we do the reaction in the lab, will we actually get 244 grams of titanium? Chances are that we won't. We will get less than 244 grams of titanium because there are so many variables, so many errors that can occur during a reaction, so many places where we can lose the product by simple causes, through simple causes that are unavoidable. So theoretical yield is the maximum amount of product that can be produced given amounts of reactants, but actual yield is the amount of the product that is actually produced after you do the reaction. So in order to calculate, therefore, the percent yield, that is actual yield divided by theoretical yield times 100. Now in this question, the actual yield is given to us as 215 grams of titanium was produced out of possible 244 grams of titanium. Therefore, that ends up being 88.1% yield of titanium rounded to 3 significant figures. Can we ever get more than the theoretical yield of the product? The answer is no. I mean, if you are getting actual yields to be higher than theoretical yield, percent yield will be greater than 100%, and that is not possible. That means something has gone wrong either in our performance of the experiment or our calculations or whatever it might be. So we need to go back and check. So actual yield can be less than or equal to the theoretical yield, but never more. Okay, let's look at another product. So here we are comparing here we are considering the combustion of a compound C5H6. Remember, please, that the first step is to write a balanced reaction equation. Please pause the recording while you do that. So that would be C5H6 plus, it'll be 2C5H6 plus 13O2 gives us 10 CO2 plus 6 H2O. Okay. The next part of the question says that if that is the case, if this is the balanced reaction equation, and if we are using those many grams of C5H6 with those many grams of oxygen, which reactant will be the limiting reactant? That's the next step in the process towards towards percent yield. Okay, so please remember we select a product to figure out limiting reactant. Now in this case, if you read ahead, let's read ahead to figure this out. If you read ahead, okay, something's if you read ahead, they're asking us for the theoretical yield of carbon dioxide. So it may be a good idea to select carbon dioxide to work with on the onset. So we need to therefore calculate 3.456 grams of C5H6, and from 8.266 grams of oxygen, we need to figure out the number of moles or grams of CO2 that can be produced. Please go ahead, pause the recording again while you complete the setup and the calculation. So that goes to 1 mole of C5H6 using molar mass, and that goes to moles of C5H6 gets converted to moles of carbon dioxide using coefficients. This gives us 0.261382544 moles of CO2. Notice that I'm not rounding off these numbers because I need to carry these numbers through to the next step. This can be converted to moles of oxygen, which can then be converted to moles of carbon dioxide. Again, using appropriate coefficients in the balanced equation, when calculated, we get. Now once again, I am not rounding these numbers, but based on these numbers we can clearly see that the limiting reactant is oxygen gas in this case, because that is capable of producing fewer number of moles of the product CO2. Next step is for us to calculate the theoretical yield of CO2. As I've said before, yes, you can leave the theoretical yield as moles if you want to, but looking at the part D of this problem, we might need to convert this into grams, because the actual yield of CO2 produced in this reaction is given as in grams. So theoretical yield in this case will be the maximum number of moles of CO2 that can be made from the limiting reactant, which is moles of CO2. We can convert that into grams of CO2, and this gives us 8.744871635 grams of CO2. Now this is the theoretical yield of CO2. Once again, I'm not going to round off this answer either, because we need to then calculate percent yield, which is actual yield given as 5.65 grams of CO2 divided by the theoretical yield 8.71635 grams of CO2 that can be made, times 100, and this percent, when rounded to the closest, when rounded to three significant figures, if you look at all the numbers in this entire problem, the smallest number of significant figures is 3, and since all we are doing is multiplication and division throughout, we'll round off our calculated percent yield to three significant figures, and that gives us 64.6% yield for carbon dioxide. Okay, so once again, the steps towards percent yield are very clear. First, write a balanced equation. Second is figure out the limiting reactant, and then theoretical yield, finally percent yield. Okay, let's go on to the next problem. Here we are dealing with fermentation of glucose to produce ethyl alcohol and um, carbon dioxide, and then they're asking us to calculate the percent yield of the reaction given the amount of ethyl alcohol that was produced during the reaction using. So please go ahead, pause the recording while you go through the process. So as I said before, the steps are very clear in such problems. First step is to write a balanced equation, which hopefully when you did matches what I'm going to get, which is glucose. In this case is going through fermentation, which is not combustion, guys. Fermentation and combustion are two very different processes. In this case, we are getting ethyl alcohol and carbon dioxide as the products in balanced form. Next step is to figure out the limiting reactant. Now, if you read this problem correctly, I hope you realized that you really need to do nothing for the limiting reactant because there is only one reactant in this process. If there's only one reactant in this process, then that reactant has to be the limiting reactant. Okay. So the next step is for us to then figure out the theoretical yield of the product, and in this case the product we are concerned with is ethyl alcohol, meaning we need to convert 90 point, please note the number of significant figures, grams of C6H12O6 to grams of ethyl alcohol. Okay, so the first step is to convert mass of C6H12O6 to grams using molar mass, and then moles of C6H12O6 can be converted to moles of C2H6O using the balanced equation, and that can be then converted into those are moles, can be converted into grams of C2H6O using molar mass of ethyl alcohol, which is 46.08 grams. When you do this calculation, you get an answer equal to 46.033966603 grams of C2H6O that can be produced. This is the theoretical yield. Therefore, percent yield will be actual yield, that is 42 grams that were actually created and isolated, divided by the theoretical yield, which is the maximum amount that could have been made, times 100. Therefore gives us 91.2369792%, which needs to be rounded to two significant figures in this case, and therefore 91% yield. Okay, here's another question, exactly the same process. However, the question is slightly different, in which case, in this case, we are given the percent yield. We are given the reaction, of course. We need to calculate the actual yield of the product in this case. Okay, so let's take a look. First step, remember, you cannot proceed if you don't have a balanced equation. So go ahead, pause the recording, write an equation. It's a combustion reaction, and balance that equation. When you do that, you get 2C8H18 plus 25O2 gives us 16 CO2s plus 18 H2O. The limiting reactant, the next step is the limiting reactant, which in this case, of course, is also made easy for you because notice that they only give us the number of, they only give us the amount of one of the reactants that this reaction uses. which basically implies that the other reactant is in excess. The fact that only the amount of one of the reactant is mentioned in the problem, you can safely assume that the other reactant is not the limiting reactant. In other words, in this case, the limiting reactant is C8H18. There is no calculations needed for you to figure that out. Next step, of course, is for us to determine the theoretical yield of the product, and in this case they want us to focus on water, so the theoretical yield of water using the amount of the limiting reactant. Now they didn't give us grams, but does that really matter? So we know that we started with 8.92 times 10 raised to 24 molecules of octane, C8H18. Now, is this a problem? No, it's not a problem, because you need to get to moles. And if you remember from your previous sessions, you can get to moles either from mass by using molar mass, or you can get to moles from particles using Avogadro's number. Exactly. So molecules of C8H18 can be converted into moles of C8H18 by using Avogadro's number. Please remember, Avogadro's number is 6.022 times 10 raised to 23. Okay, once you have moles of C8H18, that can be converted into moles of water using the equation, and then moles of water can be converted into grams of water using the molar mass of water. This calculation results in a value of 2402.267685 grams of H2O that could be made. However, they're not asking us for the theoretical yield. They're asking us to calculate the actual yield. If you remember the formula of percent yield, we can safely say that 68.5% equals the actual yield, which we do not know, divided by the theoretical yield, which we calculated, times 100. If you solve this for the actual yield, comes out to be 0.685 times 2402.267685. That gives us 1645.553364 grams. Now this final answer will have to be rounded, in this case to three significant figures based on the numbers given, and therefore when this rounds off we get 1.65 times 10 raised to 3 grams of H2O that was actually created. You do not have to write the answer in scientific notation. You could have written the answer as 1650 grams of H2O, and that's totally okay as well.